Hello everyone, myself Dr. Krishnan. In this session, we are going to discuss some important phenomena in quantum physics. Since it's a quite interesting subject and most of the people would say it is very difficult to follow. But if we can understand the basic ideas in quantum physics, then we can apply it in various applications. So before discussing about the quantum physics, we should know uh, the importance of classical physics. See, the classical physics mostly deals with the macro level, whereas the quantum physics it deals in micro level. So some important phenomena we could not explain based on the classical mechanics. There are some drawbacks that we can discuss in the upcoming slides. But still, if we can understand the basic concepts in the quantum physics, then we can use it for various applications, especially in the current era. Quantum computing plays very important role, and for all those ideas, we should have a clear basic ideas in quantum physics. Then we can play with those ideas in various applications. So in that concern, we can have some basic concepts in the quantum mechanics. There are some ideas like radiations. So, of course, we can say it's a black body radiation. Uh, Light is made up of particles. That idea needs some quantification. For that, the initial suggestion was given in 1860. It is black body radiation, followed by atomic spectroscopy and photoelectric effect. And for the wave-particle duality, the important concepts introduced in 1923 is Compton effect and uh, the electron diffraction also studied by Davison and Germer and followed by Young's double-slit experiment. And among all the important concepts given by the Louis de Broglie, he has correlated wave nature of particle as wave nature and particle nature of light with the matter waves. And by understanding the wave functions and its operators, and followed by Schrodinger, he has correlated the classical mechanics concept with the de Broglie concept and the uncertainty principle. So these are the very important phenomena in quantum mechanics. In order to understand the quantum physics, we should know the failures of classical mechanics. Classical mechanics, it has explained most of the concepts. However, it could not explain some important concepts like black body radiations. So, why it exhibits in all range of heat radiations, that it could not explain. So, it has been explained in the quantum mechanics. And the specific heat capacity of solids at low temperature, it not explained about by classical mechanics. Since we are all know, specific capacity is the amount of heat energy required to raise 1 kilogram of substance to 1 Kelvin. So that is the specific heat capacity. So at low temperature, by classical mechanics, it could not explain. And about the atomic structure, there are so many misconceptions related to atom structure. Still, people would say it is spherical in shape, oval in shape, and different structures. And yeah, of course, but still, some quite interesting concepts is there that the structure of atom is completely different. We can say it is rosette. So anyway, just I was giving some idea alone, but still, if you want, we can discuss in detail. And followed by photoelectric effect. So classical mechanics the would not explain about the photoelectric effect, since as we are all know, the photoelectric effect is very important phenomena which could be useful in various applications. See, if you take any metals, if you take any metals, when the suitable frequency of electromagnetic waves incident on the metal, it can eject the electrons. That is photoelectric effect. So whenever the electromagnetic waves incident on the metal can eject the electrons, that is photoelectric effect. And there are so many important phenomena related to photoelectric effect. By varying the intensity of heat radiation or intensity of electromagnetic waves, we can study the variations. By varying the frequency also, we can discuss about the photoelectric effect in detail. And followed by the important uh, idea is a Compton effect. Most of would say Compton effect is little tough, but according to my point of view, I could say it is the uh, little modification of Raman effect. See, as we all know, Raman effect is very important effect about why the sky appears blue in color, and even he got Nobel Prize for Raman effect also. But still, in order to understand the Raman effect, we should know if you take any substance, in specific, you can say the substance should be like a three-dimensional material. Why? Because the X-rays can undergo diffraction only through three-dimensional solids. So that is a peculiar characteristics of uh, no X-ray. It can penetrate through all the materials, but still it can undergo diffraction only through three-dimensional solid. In specific, we can say it is like a crystal. So through crystals, X-rays can undergo diffractions. See, if you take any crystal and if you are allowing some X-rays to pass through it or any electromagnetic radiations, it can undergo scattered like this. See, the concept about the Raman effect is you are allowing some X-rays or some electromagnetic radiation. Say it has the wavelength 1000 angstrom. So we can discuss this in terms of wavelength or frequency. That's based on our convenient. But still, Raman effect says that when it diffracted through a substance like a three-dimensional solid, it has some additional lines. So some lines are having no wavelength, or in terms of frequency, we can say. See, if it has frequency 500 hertz or 1000 hertz, it can be split into two of like this is 500 and this is also 500. This is for understanding, not exactly. Simply we can say when the suitable frequency of electromagnetic radiations are in specific, we can say X-ray, diffracted through the substance like a crystal, it can split, it contains two additional frequencies. One frequency is having exactly, we can say, one component is having frequency lesser than incident. For understanding, I have given 500 here, but it is not exactly, but the actual concept is in terms of frequency, we can say some components having frequency lesser than incident, some components having frequency greater than incident. This is what the Raman effect. So still, if you want to understand in detail, I could say when the electromagnetic radiation or X-ray incident on the substance and consists of some additional frequencies. In the additional frequencies, some component is lesser than incident, some component is greater than incident. So this is what the Raman effect. Of course, the difference between these two, we could say it is a Raman shift. So still, in exactly if you want to know, we can say the frequencies or the components having frequency lesser than incident is called Stokes lines. The components having frequencies greater than incidents are called anti-Stokes lines. There are some peculiar specifications behind the Stokes lines are having lesser than incident and anti-Stokes lines are having greater than incident frequency. So that we have to understand in the Raman effect. The same concept could be useful in the Compton effect in the same way. If you take a three-dimensional solid like a crystal, again X-ray photon is incident on the substance, it undergoes scattering, consists of some additional components. Like Raman effect, here also it consists of some additional components in the Compton effect. The components, some components are having wavelength same as incident. Some components having uh, components slightly uh, longer than the incident. So if it is slightly longer, then we could say that is Compton effect. So now you can understand the correlation between the Raman effect and Compton effect. But still, I can give a final conclusion. Like in the Raman effect, when the X-ray photon or electromagnetic radiations incident on any substance undergoes scattering, consists of additional components. Some components are having frequency lesser than incident. Some components are having frequency greater than incident. That is the Raman effect. Whereas in the Compton effect, some components are having wavelength same as incident, or some components are having wavelength slightly longer than incident. And again, the difference between these two, that is a same wavelength and a different wavelength, that is Compton shift. So we can discuss these two concepts in terms of frequency or in terms of wavelength. But still, it's a quite interesting concepts. And next, we can move to the matter waves. So, G. Broglie, he has given a strong uh, the proposal about matter waves. As we have already mentioned, light plays dual role. So, light plays dual role. One is the particle nature, another one is wave nature. So, De Broglie has given the strong proposal about matter waves. Like light, matter waves also uh, plays a dual role. It behaves as a particle when it is at rest, and it behaves as a wave nature when it undergoes motion. So that made a big impact in scientific science, and it is used in various applications. But still, why he has given that concepts, that bold no proposals? That is what we can say. It is de Broglie hypothesis. Since in this universe there are only two modes through which the energy can be propagated. So if you want to propagate or if you want to transfer the energy in this universe, only through modes. It can propagated only by a wave nature, or it can be propagated by a particle nature. So that made the de Broglie to give strong proposals like this. And since our universe is fully composed of light radiation and matter, so if you think about all these things, definitely will get some interest, as well as it has to be understood properly. And uh, here I would like to add some important ideas, which is uh, E equal to mc square. See how the universe is balanced. For that, Einstein has given this equation E equal to mc square. So he has used only three letters. E is the energy, m is energy, m is mass, c is velocity of light. So how the universe is balanced? For that, Einstein has used three letters. Whereas Newton, he has used three words about the balancing nature of the universe. So he says nature loves symmetry. So it just we can correlate these two. Einstein, he has given three letters to describe the wave nature of universe. Sorry, how the universe is balanced, and Newton has given three words to describe the balancing nature of this universe. So that's why we could say nature loves symmetry. But still, waves and matters are no symmetric. As we all know, every moving particle is having wave nature. Of course, it acquires kinetic energy. If we are having clear idea about these concepts, then it is very easy to understand the important derivations. Yes. So first we can discuss about the de Broglie waves and its wavelengths. So what he has done is he has correlated two important equations. As I mentioned earlier, according to Einstein, the energy equation is E equal to mc square, where E is the energy, m is the mass, c is the velocity of light. And according to Planck, E equal to h nu, where E is the energy, h is the Planck constant, and nu is the frequency. As we all know, the equation, the relationship between the velocity, frequency, and wavelength is c is equal to nu lambda. So from this, we can get nu is equal to c by lambda. So in that concern, comparing these two equations, 1 and 2, h nu is equal to mc square. So instead of nu, we can substitute c by lambda. So hc by lambda equal to mc square. Here, by simplifying this, we can. So you can cancel cc here. So you can have lambda equal to hc by, of course, you can write like lambda equal to h by mc, since we have already cancelled the c. So lambda equal to h by mc. But if the matter waves behaves as wave nature, we can use a c, since it is c is the velocity of light. If you assume it is a particle nature, then we could use v instead of c. As we all know, momentum p is equal to m into v. So momentum is the product of mass into velocity. So in that concern, in this equation, we can write like the lambda equal to h by m into v. So instead of mv, we can substitute p, since it is a momentum. So h lambda equal to h by mv, or lambda equal to h by p. So the final equation we could say lambda equal to h by mv. So this is the very important equation. Based on this, we can have some more derivations. So this is the final equation for the de Broglie wave. Next, we can move to the de Broglie wavelength in terms of energy. As we all know, if the particle is accelerated through some energy, external energy, obviously it acquires kinetic energy. So the kinetic energy is E equal to mv square, E equal to half mv square. So m is the mass and v is the velocity. So for sake of simplification, in this equation, multiply by m on both the sides. So m here, if you multiply, you can get m square. So m into E equal to half m square v square. So you can rewrite this equation like if you cross multiple, you can have 2mv is equal to m square v square. But still, in the previous slide, we have discussed about the de Broglie wavelength equation, which is lambda equal to h by mv. So in this, we need to find out mv. In that concern here, if you take a square root on both the sides, you can get root m square v square is equal to root 2me. And we can have mv is equal to root 2me. So that this me value we have to substitute in this equation, so that you can have lambda is equal to h by root 2me. So this is the de Broglie wavelength equation in terms of energy. So if you can understand these basic ideas, and it could be useful in various applications as well as in some derivations. So next we can move to the de Broglie wavelength in terms of voltage. In case if a matter is accelerated through a potential difference V, then because of some external energy, we can acquire kinetic energy. As we discussed earlier, the kinetic energy equation is of mv square, and it acquired because of the external energy are given, so that the work done on the electron is equal to E into V, where E is the magnitude of an electron. As we all know, it is 1.609 into 10 power minus 19, and V is the voltage you are applied or the potential difference you have applied. So equating this equation, E into V equal to of mv square. Again, like the previous derivation, multiply by m on both the sides, so that you can have m into EV of into m square V square. So still you can rewrite like 2 into MEV equal to m square V square. Our ultimate aim, again we have to substitute the value of mv, so that we can take a square root on both the sides. So you can have m into v is equal to root 2mev. We know m is the mass, E is the magnitude of an electron, V is the potential difference you are applied. So that mv value you can substitute in the equation. Since we know lambda equal to h by mv, it is root 2mev. So this is the de Broglie wavelength equation in terms of voltage. In the same way, we can discuss the Schrodinger wave equations. So Schrodinger, he has given some important as well as interesting ideas. He has correlated the classical mechanics, as we have already discussed these some important phenomena in the classical mechanics, and quantum mechanics is introduced, quantum physics is introduced to overcome the limitations of classical physics. So Schrodinger, he has given a clear idea, and he has correlated the classical mechanics or classical physics concept with the de Broglie concepts. And then he has obtained a new or equations, which is Schrodinger wave equation. So that is the interesting fact behind the Schrodinger wave equation, and he is the Erwin Rudolph Joseph Alexander Schrodinger. He made some important changes in the scientific era. So here we should know what is the Schrodinger wave equation. As I mentioned earlier, Schrodinger, he has connected the uh, classical mechanics concepts with de Broglie wavelength concepts. So still, Schrodinger, he describes the wave nature of particle in mathematical form. That is what we have to understand. So Schrodinger wave equation is the wave nature of particle in mathematical form. And there are two types of wave equation. First one is Schrodinger time dependent wave equation, and second one is Schrodinger time independent wave equation. See, in order to derive these two, we should have ideas about potential energy of the particle, and the initial conditions and the boundary conditions. So if we are having clear idea about these three, then it is very easy to understand the time dependent wave equation as well as time independent Schrodinger wave equation. So in that concern, first we can discuss about the Schrodinger time independent wave equation. Consider a wave in a three-dimensional, say this is the x-axis, y-axis, and z-axis. Consider a particle in any one axis. Assume that it undergoes motion. As we all know, when the particle or the matter waves at rest, it behaves as particle, it undergoes motion, it has wave nature. So the classical differential equation for any wave motion is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square equal to 1 by v square into dou square psi by dou t square. So this is the very important equation, and we could say this is the classical differential equation where psi is the wave function. So that you have to understand, psi is the wave function for a particle which undergoes motion, and x, y, z is the coordinates where v is the wave velocity and t is the time taken. So these are the important terms we have to understand. Then it is very easy to proceed further. And for sake of simplification, the equation 1 can be written as dou square by dou x square, dou square by dou y square, dou square by dou z square can be represented as del square, where del square is the Laplacian operator. It is Laplacian operator. So the equation 1 can be written as del square psi equal to 1 by v square into dou square psi by dou t square. So this is the important equation. And as I mentioned earlier, where del square is dou square by dou x square plus dou square by dou y square plus dou square by dou z square. See, for all second order differential equation, there will be a solution. See, the solution for the equation 2 is psi of x comma y comma z comma t equal to psi naught x y z into e power minus I omega t, where omega is the angular frequency, t is the time taken. So this can be written as psi equal to psi naught e power minus I omega t. So this is also an important equation. And based on this, we have to derive the remaining concepts in detail. So the equation 3, next what we have to do is we have to differentiate equation 3 with respect to time so that we can obtain the Schrodinger time independent wave equation. So differentiating the equation 3 with respect to time, that is psi is equal to psi naught into e power minus I omega t. So you have to differentiate with respect to time. So we can write like dou psi by dou t equal to minus I omega into psi naught e power minus I omega t. So this is the differentiation method. That is, you have to bring it here so that minus I omega psi naught e power minus I omega t. But still, we have to differentiate it with respect to t one more time. So if you are differentiating one more time, you can get again minus I omega psi naught e power minus I omega t. That is what dou square psi by dou t square. And in this, we have minus I omega psi naught e power minus I omega t. So instead of psi naught e power minus I omega t, you can substitute psi so that it could be easy. So you can substitute psi. So dou square psi by dou t square is equal to minus into minus plus. So I square omega square You can substitute psi here. That would be easy. But still, as we are all know, I square is minus 1. So that you have to substitute here. So that you can now dou square psi by dou t square is equal to minus omega square psi. So this is the important reaction. But still, in equation 1, if you substitute this equation 4 in equation 2, we can now see the equation 2 is del square psi equal to minus omega square by v square into psi. So simple concept is in the previous derivation, instead of dou square psi by dou t square, we can substitute minus omega square psi. That's why we are having a del square psi equal to minus omega square v square. Still, if you have doubt, I can write here the equation 2 is del square psi is equal to 1 by v square into dou square psi by dou t square. So instead of dou square psi by dou t square, we are going to substitute minus omega square psi. That's why we are getting here del square psi equal to minus omega square by v square into psi. So rearranging this equation, you can write this as del square psi plus omega square by v square into psi equal to 0. And we know in this equation omega is the angular frequency, and the angular frequency equation omega equal to 2 phi by t. This is the exact equation. So omega equal to 2 phi by t, where t is the time period. See, the frequency is defined as a reciprocal of the time period. So that's why in this equation, instead of 1 by t, you can substitute nu. So nu is the frequency. Again, as per the definition, frequency is the reciprocal of the time period, or in other words, we can say the number of rotations, number of vibrations, or number of waves produced per second. That is the frequency. That's what here it is reciprocal of the time period. That is the alternate definition for the frequency. So omega equal to, instead of 1 by t, you can substitute nu, so that you can have omega equal to 2 phi nu. So in this equation, omega equal to 2 phi nu, and as we all know, nu equal to c by lambda, or we can say v by lambda. So omega equal to 2 phi. Instead of nu, you can substitute v by lambda. If it is a wave nature, you can substitute c. Particle nature, you can substitute v. So rearranging this equation, you could write like bringing here omega by v is equal to 2 phi by lambda. That's what given in equation 6. I hope now you can understand. The ultimate aim is we have to introduce the equation for the omega. That's what. Why we have to use this omega by v? See, in this equation 5, we have omega square by v square. So in that concern, we have to find out omega by v. So if you square equation 6 on both the sides, we can get omega square by v square. It is 4 phi square by lambda square. So that in equation 5, you can write del square psi plus 4 phi square by lambda square into psi equal to 0. That we can discuss in this. Yes. So squaring equation 6 on both the sides, we can have omega square by v square equal to 4 phi square by lambda square. So that you can substitute in equation 5. You can have del square psi plus instead of omega square by v square, we are going to get substitute 4 phi square by lambda square into psi equal to 0. So in this equation, again, we have to think about the important term, which is lambda. It is nothing but de Broglie wavelength. As we have already discussed in this session, lambda equal to h by mv. So that you can substitute here. So lambda equal to h by mv. So here we have lambda square, so that you can have 4 phi square by instead of lambda square, you can substitute h square by m square v square into psi equal to 0. So substituting this value, we can have our del square psi plus 4 phi square m square v square by h square into psi equal to 0. So still we can simplify this. Again, here m is the mass, v is the velocity, h is the Planck constant, psi is the wave function, del square is the Laplacian operator. Still, in order to simplify this, we have to introduce one important concept, that is the total energy is equal to sum of the potential energy and kinetic energy. So as we all know, the total energy is E and the potential energy is V and kinetic energy is of mv square. So in the previous equation, we have m square v square. Instead of that, you have to substitute this m square v square. For that, we are introducing this total energy concept. So E equal to V into half mv square, or rearranging this. If you are rearranging, bringing here, you can write E minus V equal to half mv square. And similar to de Broglie wavelength concept, you have to cross multiple here so that you can have 2 into E minus V equal to half mv square. Again, for sake of simplification, multiply by m on both the sides so that you can have m square v square. So if you are multiplying by m, you can have m square here and you can have m here. That's what we can get. M square v square is equal to 2m into E minus V. So this equation we have to substitute in equation 9. Since the equation 9 is del square psi plus 4 phi square h square m square v square. Instead of m square v square, we are going to substitute 2m into E minus V into psi equal to 0. And still we can simplify this, multiplying this del square psi plus 8 phi square m by h square E minus V into psi equal to 0. Furtherly, we can simplify this equation by introducing the important concept which is called reduced Planck constant. So reduced Planck constant is denoted by h cross. So reduced Planck constant h cross is equal to h by 2 phi. So this is the important idea we have to understand, so that very easy to introduce here. So in this equation, you can rewrite like del square psi plus m by h square by 8 phi square, since we have a 8 phi square m here, so that you can rearrange here into E minus V into psi equal to 0. So as I mentioned earlier, introducing the reduced Planck constant, h cross is equal to h by 2 phi. We can rewrite like h square by 8 phi square as h square by 2 into 2 square phi square, and bringing to here, that is rearranging this del square psi plus 2m by h square by 4 phi square into E minus V into psi equal to 0. So here h cross is equal to h by 2 phi. If you are if you want to get h square, you can, it is h square by 4 phi square. So here, instead of h square by 4 phi square, you can substitute h cross square, so that you can have the final equation del square psi plus 2m by h cross square into E minus V into psi equal to 0. So in this equation, there is no term related with the time, hence it is Schrodinger time independent wave equation. But still, in order to derive the expression for the time dependent wave equation, we can go with the rearranging this equation. Equation 14 we can rewrite like so bringing or rearranging this, we can write this as first we can write like del square psi plus 2m by h cross square E psi minus V psi equal to 0. That's how first we can rewrite by multiplying this. And Now rearranging this, we can have minus h square by 2m into h square psi plus v psi equal to e psi. So this e psi we have to use in the time dependent wave equation. That's why we are rewriting this. So whenever we are getting the equations like minus h cross square by 2m del square psi plus v psi, then we can simply subtract e psi. And this is for the three-dimensional propagation. For one-dimensional, see, if you are using dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square, which shows that it is a three-dimensional. Whereas if you want to mention specifically a particle undergoes motion in a particular direction, say along x-axis, then instead of dou square psi by dou x square, you can use the d square psi by dx square plus 2m by h cross square into e minus v into psi equal to 0. So using this relation, we can discuss the important applications of Schrodinger wave equation. So the final equation for one-dimensional is d square psi by dx square plus 2m by h cross square e minus v into psi equal to 0. In the same way, if a particle undergoes motion along y-axis, this equation can be written as d square psi by dy square plus 2m by h cross square e minus v into psi equal to 0. Along z-axis means you could say d square psi by dz square plus 2m by h cross square into e minus v into psi equal to 0. I hope you can understand. And using this relation, we can explain the applications of Schrodinger equation, which is a particle in one-dimensional box. Before that, we can discuss the Schrodinger time-dependent wave equation. As we all know, the solution for the second-order differential equation, which is dou square psi by dou x square plus dou square psi by dou y square. So this is what we have already discussed: dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square equal to 1 by v square into dou square psi by dou t square. This is the second order classical differential equation. Sorry, the solution of yes, of course. And the for this solution is we know psi equal to psi naught e power minus I omega. Straight away you can write psi equal to uh, psi naught e power minus I omega t. Since x y z is the coordinates and t is the time taken, omega is the angular frequency. Like what we have done in this time independent wave equation, we have to differentiate equation 1, that is psi equal to psi naught e power minus I omega t. You have to differentiate it. So dou psi by dou t equal to minus I omega psi naught e power minus I omega t. Here itself we can substitute psi, that's up to you, or we can continue to this. So here instead of omega, as we have already discussed about the angular frequency, instead of omega you can substitute 2 phi nu. So dou psi by dou t equal to minus I into 2 phi nu psi naught e power n minus I omega t, or you can substitute psi here. So we can have dou psi by dou t equal to minus 2 phi instead of even yes, of course, here 2 phi I nu psi. As we are all know, according to Planck, E equal to h nu. Here we have a term which is frequency, so that we can have nu is equal to E by h. That we can substitute here. So dou psi by dou t equal to minus 2 phi I. Instead of nu, we have to substitute E by h into psi. And furtherly, we can rewrite like dou psi by dou t equal to minus I into, you can write this as E by h by 2 phi into psi. As we all know, h cross is the reduced Planck constant. Reduced Planck constant, which I have already explained, but still make sure that if you are writing, if you are using h, it is a Planck constant. If you are using h cross, it is a reduced Planck constant. So instead of h by 2 phi, you can substitute h cross. So you can have a dou psi by dou t equal to minus I into E by h cross into psi. In this equation, for sake of simplification, multiply by I on both the sides so that you can have I into dou psi by dou t equal to minus I into I, so that I square we can have I square E by h cross into psi. And as we are all know, I square is minus 1, that you can substitute here. Already we have minus here. So in the left hand side you have I into dou psi by dou t equal to, here I square is minus 1, already we have minus, so minus into minus plus, so that I into dou psi by dou t equal to E by h cross into psi. So again, rearranging this equation, you can write this as I h cross dou psi by dou t equal to E psi. See, in the Schrodinger time dependent independent wave equation, already we have obtained one equation for E psi that you can substitute here. So it is minus h cross square by 2m into del square psi equal to E psi. This is what we have already obtained in the Schrodinger time independent wave equation, that you can substitute here. And taking psi out, you can get minus h cross square by 2m into del square plus v into psi equal to I h cross dou psi by dou t. And you can uh, use some single term like Laplacian operator we have already introduced. So instead of minus h cross square by 2m into del square plus v can be denoted as h, where h is the Hamiltonian operator. So high h cross dou psi by dou t is actually E psi. So you can say h psi is equal to E psi. So this is the time dependent wave equation. Before that, in equation 7, we could say there is a term related with the time. That's why it is time dependent wave equation. I hope you can understand the time independent as well as time dependent wave equation clearly. But still, we have applications. The application is no particle in one-dimensional box. See, in the Schrodinger time independent wave equation, initially we have assumed a particle undergoes motion in a three-dimensional way, and finally we are given an application for a particle moves in a one dimension. So we can say this is particle in one-dimensional box. Assume that you are given a or we are considering a mass, that is particle which has mass m, which is kept in a deep potential well. Actually, this is the potential well. So assume a particle undergoes motion between the two ends, where the boundary condition is 0, the width is a. A particle can undergo motion like this in the potential well. But still, the important assumptions we have to consider is the potential well is having infinitely high wall. So these two are infinitely high wall, which means the particle cannot comes out. It always moves within the box itself, and it undergoes only one dimensional, but still it cannot comes out. And inside the box, the particle is having a constant potential. For sake of simplicity, it is taken as 0. This is the important point we have to understand. Let me repeat again. Inside the potential well, a particle is having constant potential. For sake of simplicity, it is taken as 0. But on the wall as well as outside the wall, the potential is infinity. That we have to understand. So in that concern, as we have already discussed, the Schrodinger wave equation in one dimension is d square psi by dx square plus 2m by h cross square into e minus v into psi equal to 0. As we have assumed here, the particle is a constant inside the potential box, potential well. For sake of simplicity, the v is taken as 0. So that the equation 1 can be written as d square psi by dx square plus 2me by h cross square into psi equal to 0. So in this equation, especially 2me by h cross square, we can take it as a constant, it is k square. So that we have to understand properly. So instead of 2me by h cross square, we can introduce a constant, it is k square. So that the equation 2 can be written as d square psi by dx square plus k square psi equal to 0. Again, equation 3 is the second order differential equation. As we all know, for all the second order differential equation, there will be a solution. So the general solution for the second order differential equation is psi of x is equal to a sin kx plus b cos kx, where a and b's are arbitrary constants. So this is the important point we have to understand, and based on this assumption, we can derive further. So this is what we have already insist. The one-dimensional box is having infinitely high wall, and as I mentioned earlier, the potential on the wall is infinity, as well as outside the wall also infinity. Inside the boxes, the potential is constant. For sake of simplicity, it is taken as 0. So this is what we have mentioned here, and make sure that the potential well is having width A. So this is very important assumption. So it is 0 to A. So that is the boundary condition where we are going to introduce apply these two conditions. So initially we can apply the boundary condition as x is equal to 0 and x is equal to A. This is the width. Now we have to determine the A and B by applying boundary conditions. As I mentioned earlier, the boundary condition, first condition is x is equal to 0 and psi equal to 0. Why psi is 0? See, initially the particle is here, that is, assume that in the left hand side of the well. If it is not moving, it will have the particle nature. So there is no wave nature since psi is the wave function. So that's why psi is 0 in the initial condition. So applying boundary condition in the second order solution for the second order differential equation, it is psi of x is equal to a sin kx plus b cos kx. So instead of psi, you have to substitute 0. X is also 0. In the second term, x also 0. So as we are all know, sin 0 0, where cos 0 1. So that it will have b alone in this, and we can get b equal to 0. This is the first boundary condition. Applying the second boundary condition, x is equal to a. So x is equal to a means a particle reached the another side here. Again, when it is reached the another side, obviously it will have a particle nature. So it is does not having wave nature, but in between, when it undergoes motion in between, definitely it acquires a wave nature. There will be a some psi value. So we are applying two extreme conditions here. So x is equal to a here. So psi equal to 0. Already b is 0. In this equation, already b is 0. Instead of x, you can substitute a here, so that you can have a sin ka equal to 0. So a sin ka equal to 0, that is the condition we are obtaining from the second boundary condition. But from this equation, we could say a equal to 0, sin ka equal to 0. As per this equation, a equal to 0, sin k equal to 0. But already the arbitrary constant b is 0, so a should not be 0. So listen carefully. In the two boundary conditions, already b is 0, so a should not be 0. But as per this equation, a equal to 0. So what we are going to do is sin ka equal to 0. So here the important idea we have to understand is sin ka is 0 only when the ka takes the value of n phi. Since we know sin n phi to n phi or whatever the orders, it is 0. So sin ka is 0 only when ka takes the value of n phi. That's what I have written the equation here. So from this equation, see ka equal to n phi. From this k equal to, we can get n phi by a. So this is the k equation. That is the represent as equation 5 here. Multiplying on both the sides, we can get k square is equal to n square phi square by a square. That we can obtain. Since already one constant k square equal to 2me by h cross square, that we have already obtained. So for that, so squaring on both the sides, we have a k square equal to n square phi square by a square. This is what we have already introduced. So k square equal to 2me by h cross square. In the equation 2 itself we have obtained. So here again, as we all know, the reduced to Planck constant h cross is equal to h by 2 phi. So listen carefully, there are a lot of difference between the h and h cross. H is the Planck constant, h cross is the reduced Planck constant. That you have to understand properly. It is reduced Planck constant. So instead of h cross square, you can substitute h by 2 phi, so that you can have h square by 4 phi square. So rearranging this again, so the 4 phi square comes here, so that we can have k square equal to 2m into 4 phi square. Already we have here by h square equal to, so here 4 into 2, we can have 8. So 8 phi square m into e by h square. This is equation 7. So equation 6 is n square phi square by a square. So you have to equate these three equations. So equation 6 is n square phi square by a square. This is equal to 8 phi square m into e by h square. So you can simplify this. You can cancel phi square here. And rearranging this equation, n square h square. So you can cross multiply here, so that you can have n square h square by 8m, and here we have a square, which is equal to e. So this is the equation for energy. This probably you would have studied in energy of an electron equation, E equal to n square h square by 8m a square. So that is what we are obtaining the energy of the particle equation. And substituting the equations 5 in equation 4, since we know this psi of x equal to a sin kx plus b cos kx. So that is the equation 4, in which we know we have obtained b as 0, so that we can get psi of x is equal to a sin kx. Instead of k, you can substitute n phi by a. That's why we are getting psi of x is equal to a sin n phi x by a. I hope you can understand. In the solution for the second order differential equation, one arbitrary constant b is 0. So this could be 0. Instead of k, equation 5 is n phi by a, so that you can have psi of x is equal to a sin. Instead of k, you can substitute n phi by a. into x. That's why we are obtaining psi of x is equal to a sine n phi x by a. So this is the wave equation. Now we have to go for the normalization of wave function. This is very important phenomena. Why we have to go for normalization? So normally, in order to determine the arbitrary constant a, we have to go for the normalization wave function. So before discussing about this, we should understand the probability condition for a particle present is psi star psi into d tau is equal to 1 for particle present. For particle present. For particle not present, psi star psi into d tau is equal to 0. This is for a three-dimensional. Whereas for one-dimensional, you can say psi star psi into dx is equal to 1. I hope you can understand. If you are using d tau, which means all the three axes, if you are using dx, it is one axis. So here psi of x is a sine n phi x by a. So psi star psi, we need to find out psi star psi. So psi star psi is a sine n phi x by a into a sine n phi x by a. So that we can have psi star psi equal to a square into sine square n phi x by a. That is the equation 10. And for that, I have already given the idea, that is integral. Actually, integral we have to use. Here also, if you are using three-dimensional, you can use the triple integral psi star psi into d tau equal to 1 for all the three-dimensional. For one-dimensional, you can use only one integral. So psi star psi into dx specifically. Along y-axis means dy. Along z-axis means dz. Particle present means 1. Particle not present means 0. So in that condition, here we are assuming a particle present and we have derived derivation based on that. So substituting this psi star psi value here, integral 0 to a square sine square n phi x by a into dx is equal to 1. So here we know sine square theta, we can introduce the sine square theta formula. Sine square theta is 1 minus, that's what I have mentioned here. Sine square theta is 1 minus cos 2 theta by 2. So that you can take out a square integral 0 to a. Instead of sine square theta, you can write 1 minus cos 2 theta by 2. That's what we have written, 1 minus cos 2 n phi x by a by 2 into dx, which is equal to 1. So still we are simplifying this. If you are integrating this, you can have sine 2n phi x by a by 2n by a. As we know, sine n phi takes value 0, so this could be 0. So that we can have a square, and we can take 2 also out. In the previous step itself, we can take that. And if you integrate dx, you will get x, and with the limit 0 to a equal to 1. So as we know, the 1 is the condition for particle present. So if you are substituting the limits, a square by 2, instead of x, you can substitute upper limit minus lower limit, so that we can have a square a by 2 equal to 1. Our ultimate aim is we have to derive expression for a square. So a square is equal to 2 by a. Taking square root on both the sides, a is equal to root 2 by a. That we have to substitute the arbitrary constant in that equation. So in this equation, instead of a, you can substitute 2 by a sine n phi x by a. And in this also we can discuss special cases. If n equal to 1, e equal to, actually the equation is n square h square. Instead of n, we can substitute 1. So n square h square by 8ma square. Similarly for 2, for 3. And this is the eigenfunction equation. The same way, eigenvalue equation is E is equal to n square h square by 8ma square. This is what you have to understand. Sometimes the question can be asked like derive an expression for eigenvalue. This is actually eigenvalue. Eigenvalue. So if they are asking eigenvalue, this is eigenvalue. Eigenfunction psi equal to root 2 by a sine n phi x by a. This is eigenfunction. But here the important concept you have to understand is if n equal to 1, we'll have only one wave. N equal to 2, you'll have two wave. n equal to 3, we'll have 3 waves. That's what in the potential box, 0 to A we have. If n equal to 1 means it will have only one wave, so psi 1. If n equal to 2 means it will have two waves like this, so psi 2. If n equal to 3, it will have three waves like this, psi equal to 3, and so on. So I hope we can understand all the concepts, whatever we are discussed in this. Thank you.